Good afternoon, everybody. Welcome to the webinar. My name is Mike Simon. I'm Director of Simulation Products here at Digital Dimensions. Today's webinar is titled Validating Your SolidWorks Designs with SolidWorks Simulation. This is part of the Simulation How-To webinar series that I host every quarter for our Digital Dimensions customers. For those of you who haven't attended my webinars before, I'd like to start off with a very short PowerPoint presentation. Then I'll go into SolidWorks, and then I'll go back into PowerPoint. I do like these webinars to be interactive, so questions are welcome. Your phone lines will initially be muted to eliminate any background noise. If you do have a question, please feel free to raise your hands in the GoToWebinar panel or type in your questions directly in the GoToWebinar panel. So let's talk about why you want to do design validation. The main reasons are the following. Design validation helps you accelerate new product development. It lets you find out if you can switch to alternate or cheaper material. It helps reduce prototype costs. And it helps you improve product quality and performance. Studies have shown that introducing validation early in the design process shortens the design cycle and helps you release a much higher quality product when the product is launched. The red curve shows a typical design process, and the blue curve shows a design process with the early design validation. When the product is launched, most of the work in optimizing the design is almost complete when early design validation is used. As you can see in the chart, the red curve is much higher than the blue curve, which means the blue curve is almost completed once it's released to production. SolidWorks Simulation is the class of products that allows you to validate your SolidWorks designs. It's broken up into three main areas. There's a subset of SolidWorks Simulation for mechanical design validation that's also called SolidWorks Simulation, and that's what we're going to concentrate on today. There's also SolidWorks Motion, which is going to be rigid body dynamics that lets you analyze things like gear motion or projectile displacements. And then there's SolidWorks Flow Simulation, which is a full-featured computational fluid dynamics package that lets you simulate liquids, gases, or even electronic cooling. SolidWorks Simulation is further broken up into different packages. The mechanical design validation package has a baseline package called SolidWorks Simulation Professional, and that's what we're going to be concentrating on today. Those features are shown in the light gray box that's on the screen. Static analyses, frequency, and fatigue are going to be the three main features I'm going to show in today's webinar. Thermal, drop test, pressure vessel, and optimization are going to be shown in future webinars. For more advanced types of analyses, there's going to be nonlinear, which lets you do nonlinear material properties, shock and vibration. For military or automotive applications, those include time history responses, random vibrations, harmonics. And then there's also composite analyses that lets you do multi-layered materials. All of these advanced capabilities are included in SolidWorks Simulation Premium, which includes everything that's in the dark gray box. An additional module is going to be the SolidWorks Flow Simulation, which I talked about earlier. It's a full-featured computational fluid dynamics package that lets you simulate any type of fluid. That includes both liquids and gases. It also helps you do electronic cooling. The example we're going to use today is the steering bracket example. This example came from an actual SolidWorks customer who was concerned about the frequent failure of a bracket in their suspension design. The bracket is loaded with 1,000 pounds from a tie bar and is made out of plain carbon steel. The 1,000 pounds comes from the tie bar, pushes on the bracket in this direction. The goal of the analysis is to make sure that the bracket is 2 times stronger than it needs to be in order to account for any type of manufacturing defects or any unforeseen road conditions. The bracket should also not fail due to fatigue, so we want to make sure it has an infinite fatigue life. We also want to make sure that it's got a high enough natural frequency, greater than 2,500 Hertz, in order to filter out any type of bumpy road conditions. So the questions we want to answer are the following. Will this design work, and how can I optimize the design to make it better? So at this point, what I want to do is I want to switch over to SolidWorks, and we'll show you how to do that with SolidWorks Simulation. Now, for those of you who don't have the software package yet, once you do purchase the software, you'll get the new simulation menu at the top of the screen, as well as the new simulation command manager. And these just gives you access to all the simulation-specific commands. Now, SolidWorks Simulation has the ability to solve for very large assemblies, but it's always a good practice to try to narrow down your problem in order to make the runtimes much faster. What I'm going to do is I'm going to switch over to the SolidWorks Configuration Manager and I'm going to switch the configuration to something called the steering bracket only. This isolates the steering bracket assembly, which contains three different parts: the steering bracket, the ball, and the pin. And the reason why we're doing that is just to narrow down the results just to this small concentrated area. We're also going to make the runtime much quicker. Okay, now once you're ready to start testing your design, the first thing you want to do is go up to the simulation menu, and let's start off by creating a study. Studies are going to be like test cases. You can name it anything you want. The first test case we're going to solve for is going to be called stress analysis. Notice all the different simulation types we have the ability to solve for. We'll stick with the default static analysis for now, and I'll click on OK. As soon as I do that, notice that the feature manager on the left-hand side changes from your design feature manager to your simulation feature manager, which is going to include any simulation-specific features. You're also going to get the stress analysis tab down here at the bottom. You can always switch the feature managers back from the design feature manager and back to the simulation feature manager. All the features, both the design and the simulation features, stay with the solid model. Okay, at this point what you want to do is you want to start at the top of the simulation feature manager and work your way down to the bottom. The first thing we're going to need to do is define the different properties of all the different parts from the assembly. So let me open up the parts folder. Notice that two of the parts, the ball and the pin, already have material properties defined. Your material properties are going to define how strong your parts are going to be. Now these two parts are made out of cast carbon steel, and that's because the original solid models were defined with cast carbon steel. If you didn't define a material with your solid models, you have the option to define your materials inside of the simulation feature manager, which is what we're going to do next. We're going to apply plain carbon steel to the bracket. And when I do that, notice that the material library is the same material library that you get with your SolidWorks interface. Okay, so now all three parts have materials defined. You can validate that by knowing that the material properties are listed on the right-hand side. You also notice the little green check marks over here. That means we've already completed these steps. Okay, let's keep stepping down the feature manager. The next thing is going to be your connections folder. There's a lot of different ways you can connect the parts together. By default, all the parts in this particular assembly are going to be globally bonded together, which means they won't be able to move relative to each other. There's a lot of different options that we have. We've got springs, pins, bolts, bearing loads, spot welds, edge welds. We can even let the parts slide or rotate relative to one another. In this case, we're just going to do a very quick analysis, and we'll just stick with the defaults and assume everything's bonded together. Let's keep stepping down the feature manager. The next thing we want to do is define the fixtures. We need to tell the software how this assembly is fixed in the real world. And the way it's fixed is it's bolted down at these three bolt holes to a larger assembly, as we saw earlier. Now to define those bolted connections, there's a number of different ways we can do it. We can come up to the connections folder, define different bolts. We can define the back planes. Like I said, there's a lot of different ways to do it. The easiest way is just to come up to the Fixtures menu, click on Fixed Geometry, and select the inside surfaces of those bolt holes. So we're basically tying down all three bolt holes. Okay, the next thing we're going to do is we're going to apply the loads to the ball. And we had 1,000 pounds coming from the tie bar. So I'm going to right-click on the External Loads folder. Notice all the different loading options that we have. Forces, torques, pressure, gravity loading, centrifugal, bearing loading, temperatures. We can even take flow effects and thermal effects from the flow simulation software. We're going to select the force option, and in the blue selection window I'll select the ball, and we want to put 1,000 pounds, but we don't want it in the direction that the arrows are currently pointing in, which is normal to the surface. So I'm going to click on the selected direction option, and I'm going to select the point on the model that's going to be parallel to the direction of the force, and I'll just click on this curve over here. And notice that the arrows automatically align to whatever geometric entity that I select. And I'll just simply type in 1,000 pounds here and click on OK. And now we've got 1,000 pounds. At this point, I'm just going to run the analysis, and the software will solve all the different equations. It's pretty quick because, again, this is a very small model. And the first result that comes up is going to be our stress plot. Now before we look at the stress plot a little more in detail, what I want to do is I want to turn off the fixtures or hide them just so it doesn't clutter up the screen. I'm also going to hide the loads. And let's go ahead and edit the definition of our stress plot. Now there's a lot of different stress components we can plot. Most people stick with the von Mises stress plot, which is going to be your resultant stress. It combines all the other components of your stress tensor and comes up with a single resultant value called your von Mises stress. I'm also going to turn on the automatic deform shape, and then I'm going to animate this thing. And this is what the animation looks like. Now the first thing I want you to notice about the animation is that the bolt holes aren't moving. And that's because we fixed those 3 bolt holes with the fixed geometry restraint. So that gives us a good indication that we've applied the restraints correctly. Now the load that we've applied was 1,000 pounds in the negative Z direction, and that was applied directly to the ball. And if you look at the ball, it looks like the ball is being pushed in the proper direction. So we've just validated that the loads and boundary conditions were applied correctly. Now with the stress chart, the blue areas are going to be your least stressed areas. The red, orange, and green areas are going to be your higher stressed areas. You want to make sure you understand where the least stressed areas and where your higher stressed areas are. And right now the higher stressed areas occur right around the restraints, just typical. But the stress path starts off at the bolt holes. Then it extends over here to this flange area, as well as over here and over here. Now, along with the color contours, the other thing you want to make sure you're aware of is the maximum stress levels in the part. The maximum stress here is 30,000 psi. And what you want to do is you want to compare that with the allowable stress of the material. Now the yield strength of plain carbon steel is usually about 35,000 psi, so we're pretty close to the limit. SolidWorks actually does a comparison for you with what's called the factor of safety plot, in case you don't remember what the yield strength is. And SolidWorks is telling us that we have a minimum factor of safety of 1.1, or more specifically, a minimum factor of safety of 1.07. That means we have 7% design margin. So if there's any manufacturing defect or any spike in your road conditions that are slightly greater than 1,000 pounds, which is our input load, we're going to be prone to failure. We might start to get some crack propagation. We may even get some fatigue failure later on during the lifetime of the product. So that's probably why the original design was not working. Remember that the manufacturer was complaining that this bracket tended to fail prematurely in the field. Now, since we found out with simulation that we've got very low design margin, we've got a couple of choices at this point. We can change the design and make it stronger, or we can change the design to include a stronger material. The easiest thing to do is to change the material. So let's go ahead and do that first. We're just going to edit the definition of our material properties, and we're going to change it from a plain carbon steel to an alloy steel. Now let's go ahead and rerun it. The alloy steel is going to be much stronger than the plain carbon steel. Stress levels are going to be about the same as we had before. Maximum stress is about 30,000 psi, but your yield strength for the alloy steel is going to be much greater. Let's see what that is by looking at the factor of safety. And the factor of safety is now 3. So we went from 1.07, which was right on the margin, to a factor of safety of 3. So we're 3 times stronger than we need to be in order to accommodate 1,000 pounds of loading from the tie bar. So at this point, our design's good enough. We know we've got more than enough margin, and we can actually go into production or go into prototype testing to make sure that this thing works. But now that we've got some additional design insight, we have the opportunity to make this thing better. Now, one of the features I like to look at with the stress plot is something called ISO clipping. And what I'll do with the ISO clipping plot is I'll take this slider bar, I'll start on the right-hand side, then I'm going to slowly move it to the left. As I slowly move it to the left, you can watch the stress areas start to grow. They start off in the bolt hole locations, then they start going into the webbing or the flanges, and then they get larger and larger and larger. You can even type in a value. For instance, I'm going to type in a value of 5,000 psi. Now everything that's colored in is going to have a stress value greater than 5,000 psi, and everything that doesn't have any color is going to have a stress level less than 5,000 psi. Remember that the yield strength of steel is going to range from a low end of about 30,000 psi to a high end of about 90,000 psi. So 5,000 psi is very, very low. And what this plot is currently telling us is this entire backside section of the bracket is carrying very little load, which means it's structurally insignificant. If you look at the top part of the bracket, we also have this area up here, as well as the area right around here, which is carrying very, very little load. So now that we have some additional design insight as to what the load path is, if we want to make this thing stronger, we can actually add material to any of the colored areas. We can make it thicker right here along this flange. We can even have a tapered thickness and make it stronger. On the flip side, if we want to make it lighter and remove material that's unnecessary, we can actually take out material that doesn't have any color. So we can remove this entire back section of the bracket. We can remove this top section of the bracket. We can even remove parts of this bottom section of the bracket, since they're going to be structurally insignificant. In fact, let's try that. Let's go back to our model feature manager, and let's see what removing material is going to do to our design. Remember, our current design has a factor of safety of 3.0. And what I'm going to do next is I'm going to basically remove some material. Let's click on the sketcher tool. I'll click on the circle icon, and basically I'm going to just draw a circular profile. The actual size doesn't matter at this point. I can always refine it later. I'll go to the extruded cut feature, and I'll just take this extruded cut and take it out about this much. And now I've got a good chunk of material that's been removed from my bracket. If I come up to our sensors function, the original mass of the model was 38.2 grams. Let me go ahead and update that to value with the new cut. And the new cut now has a mass of 34.8 grams. So about 10-15% of the mass was removed from the model. And that may be important in certain models where mass is going to be critical. You want to make sure you have as light a design as possible. So now we've got the new geometry. Let's go back to our stress analysis feature manager. Notice the little warning signs that we have here. That's just telling us that something's changed with the geometry. We need to rerun the analysis, which is what we're going to do next. I'll just click on Run. And the analysis is done. Let's go ahead and animate the stress plot. So this animation is very similar to what we saw before. Maximum stresses are still about 31,000 psi. Looks like they're slightly higher now, but not by a whole lot. The stress path still looks the same. We still get those green and red color areas that's connecting all the different bolt holes. And now let's take a look at our factor of safety plot. The minimum factor of safety we have now is 2.84. So it went from a factor of safety of 3 down to 2.84. Not a lot of change, and that's because the material that we took out of the model was structurally insignificant. Okay, we lightened the model by about 10 to 15%. Our factor of safety didn't change much. It was still at 2.8, 2.84. And if I go back to our PowerPoint presentation, our design goal is to make sure we have a factor of safety greater than 2. Okay, so let's review what we've done here. We started off with an original design. It was made out of plain carbon steel. We found out that we had very little margin, so we changed the material to a stronger material. Then we made it better by removing material that was structurally insignificant. Okay, going back to the PowerPoint presentation, looks like we took care of the first design goal. We've got a factor of safety greater than 2, and we still have some margin. So if there's some additional weight we want to remove, we still have room to play with there. The next design goal we're going to take a look at is going to be the fatigue life. Let's just make sure that we have the ability to have an infinite fatigue life, which means we want to make sure that the material does not weaken during the life cycle of the product. So let's go back into SolidWorks Simulation. And there's an option here called Define Fatigue Check Plot. And what the fatigue check plot does, and let's go ahead and type in a factor of safety of 2, is it does a quick overview of the stress levels within the part and makes sure that the stress levels do not exceed the infinite fatigue strength or the infinite fatigue life of the different materials. At this point, the software is telling us that it seems that stresses are so low that you do not need to be concerned about fatigue. However, a fatigue study can provide more insight. The software gives you the ability to specify on-off loading, which is what we have in this case. You can even do reverse loading. You can even change the material properties or the manufacturing processes of the different materials in order to change these fatigue factors. Now, if I change this from on-off loading to a fully reversed load, which means I apply 1,000 pounds, then I apply negative 1,000 pounds, then I apply 1,000 pounds, then negative 1,000 pounds, and so on, then we are going to have fatigue problems. So the software is flagging us that there's possible fatigue problems in all of the red areas. So these are going to be the areas right around the bolt holes and then right around where this flange is starting. And that's again with the on-off loading scenario. That's not what we have in this case. In our case, we just have typical on-off loading. And with the on-off loading, the stresses are low enough, which means we will have an infinite fatigue life with this particular loading condition. Okay, back to the PowerPoint. So now we know that we meet the second design goal, and that's that we're going to have an infinite fatigue life. The last design goal is to make sure that we have a frequency greater than 2,500 hertz. Most of the high displacement road conditions are going to have a frequency content between 0 and 2,000 hertz. 0 and 2,000 hertz seems to be the critical frequencies for both the automotive industry and also for military applications. So let's take a look at our natural frequencies. To do a frequency analysis, we're going to go through the same steps that we did before. We'll start off with the simulation menu. We'll come down to the study. And let's create a new study or test case, and we'll call this one frequency study. And we'll select the frequency option. And once I do that, notice we get the new frequency study simulation feature manager. The same setup as our stress analysis feature manager, but this is going to be for the frequencies. Now, rather than redefining everything as I did earlier with the stress analysis study, what I can do now is I can go back to the stress analysis study. I can take the parts, I can drag them and drop them into the frequency study. I can also take the fixtures and drag them and drop them into the frequency study. I can also drag and drop connections, the loads, the mesh, and so on. For the frequency study, that's all I need, just the materials and the fixtures. Then I'm going to go ahead and run it. And the analysis is done. The software automatically solves for the first 5 natural frequencies and mode shapes, which is what you see in the results folder. Let's take a look at the first mode shape and animate it. The first mode shape looks like this. This is telling us that our first resonance is going to occur about 2,992 hertz. The mode shape is representing the most flexible mode or the easiest way to move or displace this design. So this is the weakest mode shape. And the mode shape is greater than 2,500 hertz, which is what our design goal is going to be, which means most of the road conditions, which are between 0 and 2,000 hertz, are going to be insignificant in amplifying this mode, since this mode is far enough away from the main road conditions. Okay, one other feature I'd like to show you is once you have all these results, we now have the stress results, the fatigue results, and the frequency results. We can communicate these results to our customers or our colleagues. We can do that by saving the animation files that we just showed, and we can email those animation files to other people. The other thing that we have the ability to do is create automatic reports. There's a report function in here. Well, I'll just stick with all the default options. And what the software is going to do is it's going to create a Microsoft Word document. The Microsoft Word document is going to include all of the pertinent details of the analysis along with all the different plots that we have, and create a baseline document that looks like this. In this case, this is a frequency analysis of the suspension assembly. Again, it's got all the different files that have been used, the type of solving that we use, the number of elements, the material properties, and so on. as well as all the different plots that we've created. Then you can, of course, add your own commentary or cut and paste this into a larger report. But you've got the flexibility to do whatever you want with whatever comes out of the report generator. Okay, let's go back into the PowerPoint presentation, and let's make sure we answered all the questions. The first question was, will this design work? And the answer was no, or at least the original design did not work. We made it out of a stronger material, in which case then it did work. Then we made it better. We removed material, we made it lighter. We optimized the design by, again, changing the materials and the shape. We made sure that we have an infinite fatigue life. We also made sure that the natural frequency was stiff enough such that it was greater than 2500 hertz. Okay, I've just shown you the static, frequency, and fatigue capabilities of SolidWorks Simulation Professional on assemblies. Again, all the other features that are being shown on this slide are going to be part of future webinars. So by now you should be able to see the benefits of doing design validation, otherwise known as virtual prototyping. With virtual prototyping, you get additional design insight. You know where the weak points and the strong points are in your design. You also know where to add materials and where to remove material. With the physical prototype, you have to build the actual model and test it, and then you'll know whether the parts break or don't break. What you won't get is the additional design insight that comes with design validation. So that's the advantage of doing virtual prototyping. For this example, let's say that the initial prototype costs $2,000 and the data set up the test. For each additional design iteration, it costs an additional $500 and another data test. So for 6 different design iterations, it'll take you about 2 weeks and about $10,600 to make sure your design works. Now with virtual prototyping, it'll cost you a couple days of work and no hardware costs. Virtual prototyping significantly reduces the time and the cost to validate your designs. We have lots of customers that have used the software over the years. The software used to be called Cosmos or Cosmos Works before SolidWorks bought out the company. I was one of the original Cosmos technical managers when SolidWorks first started, and I now oversee the simulation team here at Digital Dimensions. I do software sales, I do simulation consulting, and I teach a lot of the simulation training classes. If you like this webinar, please feel free to attend future webinars. Next week I'm going to talk about electronic cooling, then fatigue, shape optimization, nonlinear materials, shock and vibration, and then composites. If you need more detailed training, we do offer training classes for both the beginning and the advanced users. We're actually one of the few resellers in the country that can support our customers with advanced simulation classes. If you want to learn more about the studies that I did today, which is again statics, frequency, and fatigue, then I'd recommend taking one of the Simulation Professional Bundle classes. I'll be teaching the next one in San Diego next month, November 15th to the 18th. So that's the end of today's webinar. My contact information is below. Please feel free to send me an email or call me if you have any simulation questions or needs. And that's it. So thanks for attending and have a good day. Bye.